Hello again everybody. In the second part of the video we are going to work about the second alternative. You know that in this series of videos I'm talking about steel structured buildings, and I have told you that mainly we have got two approaches for designing the connection of the buildings with ground, or for designing the underground levels of steel structured buildings. And in the first alternative, what we do, we construct the parts of the building under the ground, the substructure of the building, in reinforced concrete. The reason why we do not prefer to make the underground parts of the building in steel is because of the corrosion. As you know, when you left steel to get in contact with soil, corrosion may start in them, which is going to show itself with rusting. And you know that corrosion is the secret burning of the material, steel, iron. And by corrosion, the strength of steel is going to decrease. That's something we don't want. That's why in the first alternative, we construct all parts of the building under the ground entirely in reinforced concrete. And this blue line that you see here is representing the reinforced concrete basement wall and also the reinforced concrete column of the building under the ground. And above the ground level, above the ground floor level of the building, we continue the column in steel material. Whereas in the second alternative, what we do is we are constructing a reinforced concrete foundation, and we are constructing the reinforced concrete basement walls of the building. But those basement walls of the building is not belonging to the building, in fact. What it belongs is, it is acting as a retaining wall in order to stop the soil here around the building, outside of the building. But what we do not make a reinforced concrete column. So the basement walls are like surrounding walls of a building. It's like a pool made of reinforced concrete, and we are constructing the building into this pool, and the bottom of the pool is acting as the foundation of our building. This is civil engineers' favorite, because they say that the behavior of a column in which the part of it above the ground is in steel and the part below the ground in reinforced concrete, as now the column is consisting of two different materials, it is hard to predict and hard to calculate and design structurally this column member, because columns need to be continuous objects from the bottom of the building to the top, from the foundation of the building to the roof. Whereas as here in the second example, we make the column in steel material from the top of the foundation to the top level of the building in steel, which means that there isn't any material change in this continuous element, and it is now easier, and it is easier to design and easier to predict the behavior of it under the effect of loads. And in the previous video, which I have titled as Steel Structures Part 1, Wall Section Part 1, I have drawn this wall section to you, and I have explained how we tie the steel column to the reinforced concrete column. Now I found out that there is a dotted line missing here. The column is continuously in reinforced concrete from here to there, and above the ground floor level it turns into steel, and the first floor level is made of a steel concrete composite deck. And now it's time to start drawing this one. So in order to start drawing that, again what I will do is I'm going to draw a thick line here, which is representing the ground line. Let's write it here, ground line. Okay, and then what we have, we draw here a dashed line, okay, in order to show the excavation pit. Okay, and let's draw another line here. Now this line is representing the bottom face of the excavation pit. Again, so let's draw that symbol representing earth itself. Okay, so the bottom plane of the excavation pit is earth itself. And remember, I've told you that the foundation type that will be used in the building is going to be determined, is going to be designed and decided together with the civil engineers. We architects cannot determine that by ourselves. Okay, and what I say is for this building, the second alternative, I choose, it is not something a must, I choose it to be, to have a rough foundation. Okay, just to make you work on a different type of foundation system. Okay, and those dots are representing the gravel, and this thing that I represent by hatching is representing the lean concrete, and let's draw some dashed lines here in order to represent the geotextile felt, which is acting as a separation layer. Okay, and now let's draw a line here. Okay, let's extend that line a little bit more. We have earth itself at the bottom, okay, which alternatively can be called as compacted soil. Okay, and then what do we have? We have got separative layers, which is a geotextile felt. And then what do we have? We have got gravel, you can call it as blockade as well, something around 10 to 15 centimeter. In the previous video I have told you that the gravel doesn't have a constant thickness. The reason is very simple, because the layer which we call earth itself is not straight, so at some parts of our earth the thickness of the gravel coming on top of it is 10, at some parts 11, at some parts 15. Okay, so what we do, we try to make it as straight as possible. And on top of gravel we again have a separative layer. The function of separative layers is to make the gravel and the lean concrete that we will pour on top of it to stay as a separate layer for the end of their life. Okay, again a geotextile felt. This time I'm just going to write the first capital first letters of the word only. And then we have got lean concrete here. Okay, and now what we will do is we are going to place here a circle which is representing our drainage pipe. Let's write it. Okay, this is the drainage pipe, underground drainage pipe we have here. Let's use a different alternative now. Now what we have to do is we have to waterproof. We have to apply waterproofing. In the previous video I have told you to make a wall here and surround our waterproofing on top of that wall. Here I'm going to draw a different alternative. Let's say that while we are casting the lean concrete, we have made it to be slightly sloped on that line. Okay, so not very straight but slightly sloped we have, let's say. Okay, and then what we need to do now that we have got a hard plane which is a lean concrete, what we will do is we are going to cover that lean concrete with waterproofing. Unlike the previous one, this time we are not surrounding the waterproofing above around the wall, because we don't have any wall here like you see. Okay, and what we have to do now, we have to use a protective screed like this. Okay, the aim of that protective screed is to prevent our waterproofing to be harmed from the reinforcement bars and from the gravel inside the concrete, and also from the boots of the construction crew. We don't want anybody to press on our waterproofing material, because don't forget, no matter which material you use for your waterproofing, it is something around 1 centimeter or even maybe less, which means that we are talking about a very thin material which can easily be affected very negatively from the materials or from the elements that we place on them. If you press with a boot on this waterproofing material, then there is a possibility of those boots to scratch or to slice our waterproofing material, and the scratched waterproofing material is going to leak water, which we don't want. Okay, and then what we will do is we are ready to construct. Okay, let me take a a thick style. Okay, this one is our foundation, which is going to be a reinforced concrete raft foundation. Let's hatch it. Okay, this is our reinforced concrete raft foundation. Okay, it continues as a single thick layer of reinforced concrete until the other side of the building. Okay, unlike the previous one, we won't cut it from here because it is continuous. Okay, and of course what we have to do is we have to construct our basement wall right here as well. Here is our basement wall. Okay, let's remember the thickness of these materials that we have drawn them. The reinforced concrete raft foundation and also a strip foundation has a minimum thickness of 40 centimeters for 0, let's say, and the minimum thickness of this reinforced concrete retaining wall, basement wall, is going to be something around 20-25 centimeters. Let's write 25 here. And as you know, this is made of reinforced concrete, and our foundation is also made of reinforced concrete. The reinforcement bars inside them are going to be tied to each other's reinforcement bars. And concrete sticks to concrete very, very well, and we accept them to become a whole now. Okay, that's why I'm going to draw it like it's a whole. Okay, and unlike the previous alternative, the reinforced concrete, entirely reinforced concrete basement floor, this time we are ending the wall like this. Okay, because like you see here, okay, I want my ground floor to be made of steel as well. Don't forget, pink is representing steel here and blue is representing the reinforced concrete materials there. So the thing which I'm trying to say is I want that ground floor to be steel now. Okay, but before constructing or talking about our ground floor, what we have to do is we have to waterproof these surfaces as well, because you know that we are going to fill this space with soil. It will be a soil filling here, there will be a soil filling there. Okay, and in order to prevent the moisture, the underground water inside the soil filling part, what we have to do is we have to use waterproofing starting around 15 centimeters above the ground line, and don't forget to fillet this part as well. Like I have already told you, waterproofing materials don't like to turn corners. Okay, and let's fillet that part of the building as well, of the foundation as well. That's something we have to do before we pour concrete inside our formwork. And when we come to here, you see that it is not possible to tie the waterproofing materials onto each other, to adhere them tightly onto each other. That's why what we have to do now, we need to crack this protective concrete from here. Okay, so now I'm going to partially raise it. Okay, so we cast concrete there, and after we finish constructing our foundation and our reinforced concrete basement wall, this part of that protective concrete has been cracked, has been taken out from its place by ourselves, and now it is time to, or it is possible, okay, but of course let's crack it like this, okay, because you know waterproofing doesn't like to turn straight angle or perpendicular connections. And what we do is we stick the waterproofing materials onto each other at that point. Okay, and what we do, we have obtained a continuous layer of waterproofing all around our building's basement floor. Okay, but don't forget that what we need to do, we need to replace that concrete there, but this time it is named again going to be a protective concrete, because while we are filling this space, we don't want the stone and the soil to harm the waterproofing there. Okay, this is not my favorite option. My favorite option was this one. Okay, you know that. Okay, with a wall, it's much better. But in some resources, you are going to see this type of connection for waterproofing coming from the basement wall to the waterproofing underneath the foundation. So in order to show you that there are these two types of alternatives, I choose to draw that here. Okay, and what we have to do is, again, we have to place here a protective concrete. Okay, you know that we don't want, again, the soil to harm our waterproofing. Okay, and then what I will do is I am going to cover this wall entirely with my thermal insulation material, a rigid foam panel thermal insulation. Okay, not a mineral wool one, because this will be exposed to underground conditions. And I will do the same thing for here as well, like that. Okay, and again, this thermal insulation is both going to contribute to the thermal performance of the building, but mainly it will be a protective panel, protecting the waterproofing from the soil filling, especially the soil filling procedure. Once we fill it, soil will stay there forever, so it's not going to harm. But while we are throwing soil from here to there, there is a possibility of that soil and the stone inside that soil to harm the waterproofing material. So in order to prevent that, what we do is we use these thermal insulations and these protective concretes for protecting the waterproofing as well. But don't forget that this thermal insulation here is really acting as a thermal insulation because it is inside here, and we want to keep the inside at a good temperature summer winter. Okay, it will be -2 here in winter and 33 maybe there in summer. Okay, as there is a temperature difference on two sides of this wall, we need to use a thermal insulation material. Okay, and now what we will do is we are going to tie our steel base plate on top of our foundation. Okay, that's what we wanted to do. Okay, with those anchors we tie the steel base plate to the foundations. And how do we tie them? Usually we place the base plate together with its anchor rods before we cast the concrete of the foundation. Or if you say that no, I am not going to make it that quality, you can place them by opening a hole by a driller on the reinforced concrete and using a chemical anchor and then chemical wall plug, chemical anchor, and then we can place a reinforcement bar and we can weld our steel base plate or bolt our steel base plate to those anchor rods. Okay, and on top of that we are going to place our steel column. Here is our steel column. Okay, again let's assume that here, let me draw the plan view of that column profile. It's an H profile standing like that. I am looking from this side to that column, so I see this flange of that column, and this dotted line or dashed line, let's say, is representing the web part of it behind. Okay, and what we are going to do now, we are going to put our steel beam right here, okay, which is an I-shaped profile. Okay, and then let's take a thin pen now. Okay, even let's take a 0.3, maybe the brown one. Okay, and this is my main beam on elevation. Okay, and what I will do is I am going to have my secondary beam in elevation. So my secondary beam is hiding my main beam behind. Okay, and like I did in the previous video, I'm going to erase this and I'm going to convert that part of the column into a dashed line. Okay, and here is how we connect them to each other, and here is the shear tap, which is used for anchoring the steel secondary beams to the steel main beam. And let's draw here some dots as well, because this main beam that I have there, let's draw two lines to represent it is bottom flange. Okay, and the main beam is tied to the web part of the column. Okay, so the flange of this column that we have here, this plane, is hiding the entrance of the main beam into the column and arriving to the web part of my steel column. Okay, and in order not to confuse you, I'm going to erase back this. Okay, I just draw that to make you understand it clearly. And of course, okay, our column ends there. Okay, there should be an end line for our column. Okay, now what we will do, we are going to use our or place our steel cantilevered beam again. Okay, right on top of my basement wall, I place my steel cantilevered beam, and steel cantilevered beam has hidden the column behind it, so I need to convert the column at that point into a dashed line. And in order to close the floor and obtain a closed plane at the end of the floor, I use a U profile there. So it seems like this cantilevered beam and the U profile is standing above the reinforced concrete basement wall, but in fact there isn't any load transfer from this cantilevered beam to the wall beneath it. Okay, here I choose it not to have, and usually that's what we do. Okay, and what else are we going to do? We are going to place here our L profile, which is going to act as the formwork of my topping concrete, and then this is going to be my steel trapezoidal sheet, going like that. Okay, and let's draw a dashed and dotted line here. Okay, and I guess I have to extend my foundation and the other layers beneath it in order to make you understand it more clearly, or in order to make it be understood or seen more architectural. Okay, now I may draw a dashed and dotted line here as well. Okay, like that. And we have to place our reinforced topping concrete here. Okay, here's what I will do. I want to increase the length of this building because I want to place a better size of window there. Okay, this window was very small here in this drawing. That's because I didn't left enough space for the window. Now what I will do is I am going to extend my column slightly in order to obtain a larger ground floor story height. Okay, and the upper level of this building, so now we are in this level. In the previous alternative we used a reinforced concrete slab floor here. Okay, let's write it. This was reinforced concrete slab floor. Okay, you know that we have got 5 different types of reinforced concrete floor systems, and you can find the related video in my YouTube channel. Okay, and reinforced concrete slab is just one of the 5 types of reinforced concrete floor systems. Okay, but here what we do is we do not use a reinforced concrete slab floor like we did here. We have transformed that floor into a steel concrete composite deck type of floor. Again, you can find the details of steel floor systems in my YouTube channel as well. Okay, and what we will do, the first level floor is going to be same with here, and it's going to be same with this one as well. So what are we going to have? We are going to have a steel main beam here, and then what will we have? We are going to have our steel main beam there, and then we are going to have our steel secondary beam. Okay, and okay, the shear tap that we have there. Again, we have to erase this line and convert it into a dashed line, and we are going to erase this line and we need to convert that line into a dashed line as well. Okay, and we need to end the floors of the building at the same line. So here is my cantilevered beam, and here is the U profile that I use to obtain a flat end at the end point of it. And right there we are going to have our L profile. Okay, and on top of our L profile we are going to have on top of our secondary beams bordered with our L profile. Okay, we are going to place our steel trapezoidal sheet. Be careful, the steel trapezoidal sheet is touching face to face onto our steel main and secondary beams. Okay, and we cover it with a reinforced topping, reinforced concrete topping concrete, which is a reinforced concrete floor system, which is a reinforced concrete, which is made of a reinforced concrete floor material. Okay, and in the previous one I have made the wall of it as a masonry structured wall. Here I want to make it a frame structured wall. Please remember that in steel buildings, the good thing is making the building as light as possible, because light buildings will be affected less, especially from dynamic loads. And if you are living in a country like Turkey, probably you need to care about dynamic loads like earthquake very much. So light buildings is better, we can say. Okay, that's why what we do, it will be good to use a lightweight steel profile for the wall frame walls of our building. Basically we need to have two types of profiles: lightweight steel U profile, and we have to have lightweight steel C profile. Okay, CE profile, U and CE profile. Okay, these are going to be used horizontally and these are going to be used vertically, and these will be called as studs, vertical studs that we have in a lightweight steel structured wall system. Okay, let me take my thick pencil, and please, I want to take your attentions to the flash thickness of the material. The flash thickness of steel material here is around 1 millimeter only. Okay, it is like really paper thin. Okay, and what we do, we place the lightweight steel U profile right here. Okay, this is the lightweight steel U profile, and we place another lightweight steel U profile on top, and we want to have a window here. So here is a lintel made of lightweight steel, and here is the top level of my parapet wall. And of course they are tied to each other with the help of my lightweight steel CE profiles, like that. Okay, they touch face to each other, and we are talking about 1 millimeter thickness of a material. So here they are like they are overlapped onto each other. Okay, and of course, in order to say that it is a wall, it is an equivalent of a masonry wall, what we have to do is we have to use here an acoustical insulation. Okay, glass wool blanket maybe, and we have to use the same glass wool blanket here. Be careful, I didn't name it as a thermal insulation material, I just name it as a acoustical insulation. Of course it is going to contribute to the thermal performance of the wall, and it's going to make this wall equivalent with a masonry wall. Originally this wall didn't have any mass, and it is not performing well as the masonry wall performs in terms of thermal performance and also, and more importantly, acoustical performance. But this thermal insulation that we use here and that thermal insulation that we wrap the entire building is not the same, which means that the thermal insulation that we have here is going to climb up and cover our walls as well as a second layer. Okay, and both sides of this frame will be covered with a board. Remember what type of boards do we have? We have got three main types of boards: wood boards, gypsum boards, and fiber cement boards. Okay, and boards are surface generators in construction industry. With boards we generate a surface, and now with the help of these boards that we use there, we generate the wall plane. Okay, and then okay, let's say that we want to use a more sophisticated external wall finishing here. Here in this example we have used an attic wall system, which is externally thermal insulated one, and a plaster externally thermal insulated composite external wall finishing, which means that the thermal insulation panels are directly covered with a plaster and then they are just painted. Okay, it's a very simple and very common type of external wall finishing system used in normal simple buildings. Okay, but if we want to make a better looking building, not a plastered and painted finished building, we may use a cladding. Okay, what type of different claddings do we have? Okay, we can use a ceramic tile as a cladding, we can use a stone tile as a cladding, or we can use a timber panel as a cladding as well. We can increase the number of them, even glass can be used as a cladding maybe. Okay, here let's say that we cover it with wood, and from outside we want the building to be seen as it is finished with wood material. What we need to think about now, okay, claddings need to have a substructure. And what's a substructure? Substructure is an extra structure that we mount to the main structural system of our wall, and which is specially placed for carrying the finishing materials, claddings of ourselves. Okay, and here, as we want to use timber, the substructure is going to be good to have to be made of timber as well. Okay, so what I will say is, let's have a wooden button of 5 by 5 to act as a substructure for our timber cladding. Okay, and what will I do? I'm going to mount this 5 by 5 timber button to my C profiles behind. Okay, and how am I going to do that? I'm going to do that by using a steel bracket. Okay, a steel bracket is like an L profile. Okay, but the width of it is small. Okay, let's say that is 5 centimeter here. It is one length is let's say 10 centimeter, and its height is again 5 centimeter only. Okay, and what we do, we are going to use it. We are going to turn it 90 degrees there, and from the side we are going to see it like this. Okay, so this is the side view of our bracket, and this is the top view of it. Just a second. Top view of it is going to be something like this. Okay, I guess I have to erase this line. Okay, this is the top view. And what I will do is I'm going to mount it here. Okay, here is one. Be careful. It seems like it has been tied to my board, but it is not. From the top of my board, it is tied to my CE profiles. Like that and like this here. Okay, and then what? Then I'm going to take this button and I'm going to upside it down 90 degrees. So it will stand vertically like this. Okay, and I'm going to tie it to here. Okay, sorry, just a second. This final bracket is slightly smaller than it should be. Okay, what I will do is I'm going to extend it slightly. Okay, and I'm going to draw a line here. This is my button going all the way down, 5 by 5 button, and the final bracket is longer than it should be, I guess. Okay, so here is my button, and I'm going to end it right there. Okay, do you understand? What I did is I have used screws here, okay, in order to hold the button. Okay, so my pencil is now the button, and the brackets are holding the button like this, and another one here. Okay, I have tied them to the wall structure. Okay, and what will I do? I'm going to extend it until the top. Okay, and let's not end it. After we study the roof structures, we are going to look what will happen to our cladding. Okay, at this stage I'm just ending it like this. Okay, it continues up, but here I choose it to end right at the end of my view profile there. Okay, And what about the timber cladding? Timber cladding is a massive timber board, okay, with a height of 15 centimeter and a thickness of 2 centimeter and the length up to what you like, let's say 2 meters. Okay, and what will I do? I'm going to bring it here and nail or screw it to my buttons. Okay, but this will be the window opening, so I am going to stop putting it there and I am going to continue putting it on top of my window opening. It goes on like this. Okay, and what will I do now when I come to here? Okay, I am going to erase this line, okay, because I will not be able to see the button. Okay, but instead I am going to see my wooden cladding turn inside my window opening and reach to my window. Okay, so but where is my window? Okay, here is my windows blind frame. Okay, but we forget something, I guess. Okay, so what we have is between the buttons we want a ventilation space. We probably in the lectures we have talked about ventilation spaces and air spaces, air gaps or ventilation gaps. Okay, ventilation space, ventilation gap and air gap. Okay, ventilation gap is for preventing condensation risks, okay, and air gaps are for bettering thermal performance, acting as a thermal insulation, bettering thermal performance. Here I want to have a ventilation space because I am afraid of the humid and warm air penetrating into my wall, condensating at this level behind my behind my timber claddings. Okay, and the great risk of condensation is going to occur right here. What do I have here? I have my thermal insulation. Okay, again I use the thermal insulation continues here, but the cladding that turns into the window opening is hiding it beneath. Okay, and I do not draw it, and I have my thermal insulation going like this as well. Okay, let's make here slightly larger. Okay, and now what do I have right here? I want to hatch it with orange color. Okay, this gap that we have here and this gap that we have here is the air space, ventilation space. Okay, so air, what air? Fresh air can enter from there and it can exit from there from the top. Okay, and fresh air is going to dry the humid and warm water, humid and warm air coming inside the building, and it's going to prevent the condensation to occur. Okay, and now let's continue with our blind frame. Here are our blind frames, and now that we have blind frames, what we have to do is we have to turn our thermal insulation until my blind frame, like that. Okay, and here is my window frame. I tried to make my window large, but I couldn't. Sorry about that. Okay, again, I just have a very small window left. Okay, in normal conditions, the window is going to be something around 1 meter in height, but I guess it works. Okay, and what now we have to do? Firstly, the section of the cladding turns like that, and we turn the wooden cladding in section again. Okay, so these are all in section. These are wooden claddings that we have, and this is wooden cladding that we have here as well. Okay, and this, let's extend the wooden cladding until there, and this is my metal external window sill. Okay, and these things that you see here are the elevation of my cladding. Okay, and the final elevation line is here, and here I'm going to place a stone, maybe natural stone, internal window sill. Okay, so what layers do we have here then? Let's draw a line here and let's turn it up. Okay, what is the most inner layer? Let's assume that it is a board. It is a board, but let's assume that it is a gypsum board. Okay, with a thickness of 2 centimeters. 2.5 in fact, 1.25 each, a total of 2.5. Let's make it 2.5. Okay, and then what do we have? We have, okay, I want to erase this. Okay, I want to write it more easily and in a more proper way. Okay, so on top of my gypsum board I have my acoustical insulation. The acoustical insulation is standing in between with a 2E CE profiles. Okay, I have the CE profiles are in the background. Don't forget that these types of representation of text needs to show only layers. Okay, and a stud is not a layer, it's an individual component, so we need to pass the section plane not from the stud but from the continuous layer, which is the acoustical insulation here. And next to that, again, the acoustical insulation here is, let's assume, to be 8 centimeters. Okay, because let's assume that we use a frame structure of 8 centimeters only. And then again we have got 2.5 centimeters of gypsum board. Okay, let's write it full. Okay, and then what do we have? We have got a mineral wool thermal insulation, which is entirely wrapping the building. So now this is the thermal insulation. Maybe these two are same material, but what we do, we name them differently because this is thermally insulating the entire building. This is just insulating the wall. That's why we name it acoustical insulation, but of course it's going to contribute to the thermal performance of the building. And the mineral wool thermal insulation is also going to be, let's assume, 5 centimeters only. And then, now that we have a ventilation space there, we are afraid of water penetration from outside, from the cladding, and we want to protect our thermal insulation against getting wet. That's why we have to use a permeable waterproofing here. It doesn't have a thickness because it is just a very thin sheet. Okay, and then on top of permeable waterproofing, what do we have? We have got our ventilation space. How much of a ventilation space are we talking about? We are talking about 3 centimeters of a ventilation space. It will be enough. And then we have got 2 centimeters thickness of a wood, of a timber wood. I use here timber, I don't know why. Okay, timber wood cladding. Timber or wood, of course, not timber wood, but timber and wood, they are same thing. Wood cladding we have. What is this? Let's make a quiz. Okay, you are right, it is the steel column. And what is this we have here? It's also the steel column. Okay, what do we have above the lean concrete? We forget to lengthen our waterproofing here. Okay, and what do we have above the lean concrete here? Okay, we have, okay, I'm not going to write the full names. We firstly have the waterproofing, and then we have the protective concrete, and then we have the raft foundation. Okay, the thickness of raft foundation is 40. The thickness of protective concrete is 5 centimeters, let's say 5.8 maybe. Okay, the thickness of waterproofing is around 1 centimeter. We haven't determined the material that we use as a waterproofing, so let's say that it's around 1 centimeter. Maybe some less, maybe some more, it doesn't matter. And above the raft foundation, let's cover it with a screed again and straighten the plane. Okay, screed of 5 centimeters, and then let's cover it with wooden parquets, let's say. Okay, let's make massive wooden parquets, which is glued to the screed with a thickness of 2 centimeters. Okay, and what layers can we put here? Okay, so again, let's put a screed there. Okay, and this time above the screed, let's put a layer of mortar and let's cover it with stone. I don't know why, but in the ground floor, I prefer to have a stone finishing. Now, okay, so what do we have here? We have the steel trapezoidal sheet. Thickness of it is around 1 millimeter. And then we have got reinforced topping concrete, and then we have got mortar, which is used as a glue to glue our marble flooring. Okay, that's all. This is the second drawing I expect you to draw and upload to the related course management system that you use in ITU and in Bahçeşehir University. Okay, that's all. See you later. Bye bye.